Welcome to the lecture on suspensions. In this lecture, we will be looking at the pharmaceutical applications of suspensions, formulation of suspensions, additives, and manufacture of suspensions. First, let's look at what a suspension is. A suspension contains fine, insoluble solid particles, which we call the dispersed phase, dispersed in a fluid, which we call the dispersion medium. The particle size of the solid material can affect its physical and chemical behavior, so a distinction is usually made between a colloidal suspension, which contains particles up to 1 micrometer in size, and a coarse suspension, which contains particles larger than 1 micrometer. Most of the pharmaceutical suspensions are coarse suspensions. A suspension appears cloudy because of the solid particles in it. Insoluble drugs may be formulated as suspensions for administration through various routes, such as the oral route, for topical use, such as calamine lotion, parenteral preparations, as well as ophthalmic preparations, such as eye drops. Ideally, a suspension should have uniform dispersion, where the solid particles are evenly suspended throughout the liquid. If the particles were to sediment, they should be easily redispersible by shaking the bottle. Viscosity is also important in suspensions. The solid particles should be small and uniformly sized, and the drug must be stable when surrounded by water. If a drug is insoluble or poorly soluble, a suspension would be a suitable dosage form. If a drug is unstable in water, then a different form of the drug that does not dissolve in water may be used in the preparation of a suspension. Some drugs, such as antibiotics that are unstable in water for extended periods of time, are supplied as dry powder mixtures, and water is added just before dispensing it to the patient. In suspension, the drug particles are very fine. This provides a high surface area for dissolution and absorption of the drug. Suspensions are also useful for improving the taste of products, since the taste of most drugs are less noticeable when they are formulated as suspensions compared to solutions. Besides oral suspensions, some topical preparations such as calamine lotion are also formulated as suspensions. Parenteral preparations can also be formulated as suspensions to control the rate of absorption of the drug. For example, NPH insulin is formulated as a suspension. When it's injected into the fats under the skin, insulin will be released slowly from the solid crystals. Vaccines are also formulated as suspensions, and X-ray contrast media that is used to help to visualize the stomach and intestines are also formulated as suspensions. The most important consideration in the formulation of suspensions is the size of the drug particles. Particles of smaller size would sediment more slowly and uniformly. Also, if the particles are too large, exceeding 5 micrometer in diameter, they would impart a gritty texture and cause irritation, especially if the suspension is to be applied to sensitive tissues such as the eyes. With parenteral suspensions, particles that are too large may block the needle. Particle size also affects the rate of release of the drug and its bioavailability. The sedimentation rate of particles in a suspension is influenced by several factors. Stokes' law shows that the rate of settling is related to the diameter of the particles, the density of the particles and the medium, and the viscosity of the medium. Clearly, the greater the diameter of the particles, the faster the sedimentation rate. Therefore, a slower rate of settling can be achieved by reducing particle size. The sedimentation rate is indirectly related to the viscosity of the dispersion medium. Therefore, by increasing the viscosity of the dispersion medium, the rate of settling is reduced. Keep in mind though that a very high viscosity is not desirable either because it is difficult to pour and to redisperse. Both attractive and repulsive forces exist between particles in a liquid medium. When materials are reduced in size, they gain a large surface area. This gives the particles a high surface free energy, which causes the system to be thermodynamically unstable. There is therefore a tendency for the particles to regroup to reduce the excess free energy of the system. At the same time, when materials are suspended in a liquid, the particles acquire a surface electrical charge. The particles are surrounded with ions of the opposite charge. Like charges repel, therefore there is an electrostatic repulsion between the particles. If the net attractive forces between the particles exceed the repulsive forces, a flocculated suspension is formed. The particles approach each other and form loose aggregates called floccules. Floccules sediment quickly, and a large volume of loose sediment is formed with liquid entrapped in the floccules. With the sedimentation of the particles, the supernatant, which is the liquid above the sediment, becomes clear. An advantage of flocculated suspensions is that the particles are easily redispersed by shaking. However, it has an unsightly appearance. There is also a risk of inaccurate dosing if the patient does not shake the bottle to redisperse the sediment before use. On the other hand, if the net repulsive forces exceed the attractive forces, the particles remain dispersed and form a deflocculated suspension. These particles sediment very slowly. However, when they do sediment, they form a compact solid layer or cake which is difficult to redisperse. Since the particles do not all settle together, the supernatant remains cloudy for a long time. The advantage of deflocculated suspensions is that it appears elegant compared to flocculated suspensions, but the disadvantage is that the sediment is difficult to redisperse. The formulation of a suspension depends on whether the particles in suspension are to be flocculated or deflocculated. One approach is to increase the viscosity of the vehicle or liquid to keep deflocculated particles from settling. The second approach is to use flocculating agents to produce floccules so that although floccules settle, it is readily dispersible. Several factors are considered when formulating a suspension, and I will be discussing some of these. The drug particles in a suspension are obviously not very soluble. Most insoluble solids are hydrophobic or water-hating and cannot be easily wetted. Just to explain what wetting is, if water does not spread over the solid surface of the material, like in this case, then it is poorly wetted. If water can spread easily across the solid surface, like in this example, then that material shows good wetting. Back to the particles in a suspension. If the particles are not easily wetted, they tend to either form clumps, remain on the surface, or get stuck onto the walls of the container. Wetting agents can be added to promote wetting of the particles, and they work by reducing the interfacial tension between the solid particle and the liquid medium. Examples of wetting agents are surfactants such as twins, spans, and sodium lauryl sulfate, natural polymers like acacia, or clays such as bentonite. When using the flocculation approach, a flocculating agent is added to the formulation. Flocculating agents work either by neutralizing the surface charge on the particles and therefore reducing the repulsion forces, or by binding to two or more particles, forming bridges between them. Flocculating agents could be electrolytes such as aluminium chloride, polymers such as PVP or cellulose derivatives, or surfactants such as sodium lauryl sulfate. In both flocculated and deflocculated suspensions, viscosity modifiers, which are also known as suspending agents or thickening agents, are useful for increasing the viscosity of the liquid medium, thereby reducing the settling rate of the particles. Examples of viscosity modifiers are polymers acacia, tragacanth, methyl cellulose, and hydroxyethyl cellulose, as well as clays such as bentonite. The aqueous medium containing suspending agents and sweeteners is a good medium for microorganisms to grow. Hence, preservatives are also added to prevent microbial growth. Other additives may also be required, and these are similar to the additives in solutions. With suspensions, the rheology or flow of the suspension is important. Ideally, a pharmaceutical suspension should exhibit high viscosity when it is not being stirred or shaken. This will mean that during storage, the high viscosity reduces the settling rate of the particles. On the other hand, at higher shear rates, for example during stirring or shaking, the suspension should exhibit lower viscosity. This will mean that after shaking of the bottle, the low viscosity allows the product to be poured out easily. Many polymer solutions and suspensions show shear thinning behavior, which means the faster they are stirred, the less viscous they become. Some polymers and clays also confer thixotropy, which means that the longer the liquid is stirred, the less viscous it becomes. Suspending agents that are pseudoplastic and thixotropic are useful in the formulation of suspensions. The bioavailability of a drug formulated as a suspension depends on how quickly the drug can dissolve and diffuse to be absorbed by the body. This in turn depends on the size and shape of the particles, the polymorphic form used, and the viscosity of the suspension. Lastly, let's take a look at how suspensions are manufactured. In the lab, suspensions are mixed using a mortar and pestle. The powdered drug and excipients are first mixed, then the liquid portion is mixed in slowly. Finally, the suspension is made up to the correct volume with the liquid vehicle. On a large scale, the process may be slightly different depending on the formulation of the suspension, but in general, the drug particles are mixed with a small portion of water that contains the wetting agent. At the same time, the suspending agent, which we also know as thickeners or viscosity modifying agent, is dissolved or dispersed in the main portion of the vehicle. Subsequently, the wetted drug particles are mixed with the dissolved suspending agent. Other excipients such as electrolytes or buffers are introduced. The preservatives, flavoring agents, and coloring agents are added last. Finally, the formulation is processed with homogenizers, ultrasonic devices, or colloid mills to produce a uniform product. We've come to the end of the lecture on suspensions. In this lecture, we've looked at the pharmaceutical application of suspensions, formulations of suspensions, which can be classified into flocculated and deflocculated suspensions, additives used in suspensions, and the manufacture of suspensions.